So what we've done is we've transformed this partial differential equation into this partial differential equation by changing from xy coordinates to xi eta coordinates, where we're free to choose what xi and eta are. Now the coefficients of this differential equation are quite complicated functions of the coefficients of the original, but in principle we know what they are. And now our question is, can we simplify this? Choose a coordinate system to simplify this. And the answer is yes. And the terms we choose to simplify are the second order derivative terms. So we try to set A and C to be 0, so this is the only second order derivative in the PDE. Okay, we can do that and we know the expressions for A and C. They are these: A xi x squared plus B xi x xi y plus C xi y squared. Similarly for C. And our aim is to choose xi and eta such that these are 0. So divide this A equation by xi y squared, so that we need A xi x over xi y squared plus B xi x over xi y, because there's already xi y there, plus C is equal to 0. Divide the C is equal to 0 equation by eta y squared. And then we get A eta x over eta y squared plus B eta x over eta y plus C has to be 0. Now the great thing about these equations is they're exactly the same form, so if we can solve one, we can solve the other. And also, they are a quadratic equation for the as yet unknown ratios, xi x over xi y and eta x over eta y, and we can solve quadratics. You know, it's the famous formula. So, in the hyperbolic case, when delta, which is b squared minus 4ac, is bigger than 0, the solution is real, which is what we want, and we can then say that xi x over xi y and or eta x over eta y are the quadratic solutions of this, namely minus b plus or minus the square root of this discriminant over 2a. So there's two roots of the quadratic. We've got two things, so that to be equal to that, so let one be one and the other the other. Right, so we choose xi x over xi y is equal to minus b minus the square root of delta and 2a, and eta x over eta y to be the other one, minus b plus the square root of delta over 2a. In other words, what we want the coordinate system to satisfy is that the xi by dx is minus b minus root delta on 2a dxi by dy, and we want eta x is minus b plus root delta over 2a the eta by dy. And these are two differential equations for the two unknowns of our desired coordinate system, in which a and c go to 0. Now let's rewrite these a little bit. We let lambda 1 of x and y be essentially the negative of this coefficient. I'll squeeze it in, minus lambda 1. In other words, lambda 1 is b plus root delta over 2a, and we want this to be minus lambda 2, So lambda 2 is equal to b minus the square root delta over 2a. And when remembering these formulas, remember it's like the quadratic, but it's plus b. Okay, so what that does is, okay, the right hand side is minus lambda, so move that onto the left hand side and you end up with this pair of differential equations, namely dxi by dx plus lambda 1 of xy dxi by dy is 0, and d by dx plus lambda 2 of xy d by dy is equal to 0. And our next challenge will be to solve these in any scenarios and find the coordinate system that simplifies this PDE.